Recording in progress.
Okay, great. Here we go. All right, so we're doing the 8.2 lesson today, and we're on page 5, graphing simple rational functions. It says simple because they are simple. And rational, I'm going to explain what that means just a little bit, why we're calling these rational functions. It is going to get more complex next week. So if you happen to miss class, talk to me. I'll help you out because we're spending 2 days on 8.3. That's how intense it gets. But anyway, for now, let's just do a little review. So direct variation, remember what that means, is that y equals k times x, or y over x equals k. Remember, k is a constant. K is a constant. So x and y should be a constant ratio. So if I divide x and y, it should always be the same.
Is that only for direct?
100%. Sorry for a lot of writing, but I want to make sure we're clear on this, right? So direct is y equals k times x, or y over x equals k, move x to the other side, right? K is a constant. Since k is a constant, that means y over x is a constant ratio. Because that's a ratio, right? Ratios we divide, right? And, or in the more layman's term, if you divide y by x, or x by y, if you do x by y, it doesn't matter if you do the other way around. But it should always be the same. So let's look at these two tables here now. If I did y divided by x for a, what happens for the first row? If I do y divided by x, what do I get? 5. 10 divided by 2. 4 divided by 20 divided by 4. 35 divided by 7. 5. Come over here. 6 divided by 1, 6. But then 3 divided by 2? No. And no, so forget. So definitely the direct variation is going to be A.
Does that mean B's inverse?
B will be inverse. So definitely the direct variation will be for A. Because if I divide y by x every single time, I get the same thing. This question actually does show up on the SAT, just so you know. What they do is they'll have like 4 choices, so I'll have 4 tables, and they'll say which of the 4 tables is better page. I've seen that. It's easy if you know what it means. It's not hard. Just gotta know what it means. So A is definitely direct. So we're good on that? Okay. Now inverse is the other way around. We'll switch colors for a bit of contrast. So inverse is the other way around. Instead, actually, I'll just clear the screen. Can I clear the screen? We're good? Right. Inverse is the other way around. Y equals k over x. Or x times y equals k. So in this case, you're going to have a constant. That's your constant, right? So x and y form a constant product. So what this means, if I multiply x and y, the result should always be the same. And notice that's just the opposite of division, right? Instead of dividing, we're multiplying. Hence the name inverse. Should always be the same. So now, what happens when I multiply each of these pairs? What do I get? 6 at a time. You're not going to fit that over here. You have to go over here. Also, what happens when 6 goes to 3? That's when 6 gets halved, right? What happens to the x guy? It gets double, right? Inverse. That's what it's called inverse. Instead of multiplying, now we're dividing, or vice versa. So in this case, for part B, that's inverse. Okay, what we're going to do today is graph inverse type relationships. That's what we're doing today. So a simple rational function, and can I clear? Okay, a simple rational function looks like this. Y equals A over X minus H plus K. And the parent function is Y equals 1 over X, which is inverse variation. So today we're going to be graphing this now. But in general terms, it's going to be this: Y equals A over X minus H plus K. And the parent function is 1 over X. Now, if you have 1 over X, then what is H and K then for this equation here? You have Y equals 1 over X. So A is 1, of course, right? So there's no stretch, right? Because A doesn't stretch in the reflection. 0. H is 0 and K is also 0. So there's no movement. In fact, actually, if I go to give me one sec here. If I go to Desmos. Here we go. Y equals, oh, sorry, screen's frozen. Here we go. Okay. We go 1 over X. It's a really weird graph, right? That's Y equals 1 over X. It's a really strange graph. And this is on the notes right now. I'm going to do the problem. Yes. We talked about asymptotes in the previous unit. Asymptotes are a big deal. That's why next week when it gets more complex, I need 2 days to do 8.3 because the asymptotes get really, really wacky. Yes, 2. You could have like 3, 4, 5, 6 infinite asymptotes. So it does get really wacky. But really quickly here, can I plug in 0 into this equation? No, right? So that's undefined. And that explains why you have a vertical asymptote right here. You can't plug in 0. What if I plug in 1? What do I get? No. So the one I'm doing on the screen right now. We'll come back to notes and stuff. We're stepping away from notes just for a little bit. If I plug in 1, I get 1, right? What if I plug in 2? Half. What if I plug in like 100? Which is tiny, right? And if I plug in -1, I get -1. -2, I get -half. -100, I get -1 over 100, which is -0.01. So you see how the graph like it? So it's almost like kissing the x-axis, but it gets really close to it, right? It's like almost grazing it, right? As you go off in this direction, that direction. But when you get like, if I were to clear my screen, like what if I were to plug in? What if you're playing 1/2? What would y equal now? What's 1 over 1/2? That's like 1 divided by 1/2, right? What happens if you divide fractions? You flip the second fraction, you get 2. What if I plug in 1 out of 100? What would I get? You get 100. So do you see why the graph goes haywire as you get closer to the y-axis? It starts shooting up forever, shooting down forever. So we're going to be exploring that kind of stuff with these kind of functions. And this is the parent function, by the way. So then you could see that if I were to do this, right, like if I were to put a +1, what's going to happen when I put a +1? You shift it up 1. What if I change it to a -1? Shift down 1. Or what if I put a negative out here? Flips. What if I put a 2 here? It stretches. What if I put a -1 on the inside? Goes right. Goes left. It's all the same stuff we've been doing previously. But the asymptotes are going to be a big deal because asymptotes set the foundation for the graph. And kind of not really.
Wait, so this one graph has 4 asymptotes?
Yeah. No, 2 asymptotes. Sorry, 2.
It's 0.
Well, let's do some examples. Right. But what we're going to do next week could have multiple, like 3 or 4 or 5 or 6. Hmm? What do you mean by limitations? I mean, it just depends how it's set up. I mean, like for example 2 can't pass the y-axis because I can't plug in 0 for x. It depends. Yeah, it really depends. But let's work on this one right now. Let's plug in some numbers. If I plug in -3, what do you get? So now let's go back to notes. Plug in -2, of course, get -3, -6. Undefined, right? That can't happen. Can't divide by 0. And of course, 6, 3, and 2. Plot the points. That's easy peasy. -3, -2 is right here. You won't be able to. And then, of course, 1, 6, 2, 3, and 3, 2. So you get something that looks like this, right? Now, very, very important. Very, very important. You have to have the asymptotes. So you have a horizontal asymptote at y equals 0. You have a vertical asymptote at x equals 0. -1? I said x equals 0.
That's an arrow.
This is why you should audit your notes, because my handwriting sucks. So, or ask questions. Thank you, Haley, for clarifying. And or AJ for very important though, you have to have asymptotes done correctly. Now, what you don't want to do is be sloppy with your work, right? So coming back here again, before I drew the curves, actually, no, let me go back. Don't be sloppy and draw your curves. You want to be somewhat accurate. Don't do this. Some people will draw this, and then they'll just get kind of sloppy and do that. Then what you're telling me is that y could equal 0. Right? When we cross the x-axis, we know y equals 0. We know this. So you're telling me that 6 over x could equal 0. So you're telling me that 6 could equal 0 times x. What's 0 times a equal? Exactly, right? Numerically, you guys know that. Right? So graphically, don't do that. Right? Don't do that. So you got to be very mindful when you graph things that, oh, okay, this is getting closer and closer. Y equals 0. Because you think about what happens when x is really large. And this gets really, really big. Y gets really, really tiny. But will y ever get negative? I mean, it's positive divided by another positive number? Absolutely not. No way. Right? It gets like 0.0000000, like really close to the x-axis, but never ever that's to be negative unless I make that negative.
So does that mean our domain of range is always going to be
all real except 0?
all real?
Yeah, I'm going to get to that in a sec. But yeah, that's good you brought that up. But like, what if I plug in -1 million? Same thing, right? Like, I can't have this. I can't do this and have it cross the x-axis. That makes no sense, right? It's got to get really close to it. And of course, you can't plug in 0, right? Like, if I plug in super small numbers, what if I plug in something really small? Like, say if it's 6 over 0.00001, I'm going to get 60,000, right? I think 60,000. I think I got that right. So if I put in a super small number, it gets really close to y-axis, but it doesn't cross it, right? Because what does it mean to have y-intercept? What does x equal when we have y-intercept? 0. Can I do 6 divided by 0? No. It's undefined, right? That's and the reason why you can't do 6 divided by 0. Can you multiply 0 by something and get 6? No, you can't. So you got to be very careful when you do these. Don't be sloppy. This is why I'm spending a lot of time with this stuff, because this is actually a big part of calculus. When you guys, I know calculus is a year and a half from now, but when you do move on to that level, you got to know how these graphs look and how they behave, because you're going to be applying calculus principles to these types of functions. A lot of things are modeled using this kind of function. And another thing I forgot to mention: why are we calling it rational in the first place? Why are we calling it rational in the first place? Because it's a ratio of two expressions. That's why it's called a rational function. It's a ratio of two expressions, right? You have 6 over x. That's why it's called a rational function. And again, let me redraw the curves again. Remember, the curve looked like this, right? Curve looked like this. And we had asymptotes, right? So this is a ratio of two expressions. More specifically, expressions that are somewhat polynomial in nature. So you have to make sure that like x raised to some whole number or just a number up above, down below. Remember, the horizontal asymptote was y equals 0. Vertical asymptote was x equals 0. And domain. Let's talk about domain and range really quickly. So I could plug in any x value except what again? Except 0. So your domain would be this. And looking at the graph, I could obtain any y value except which one? Except 0 again. Yep. Yeah. Union. So it's a U.
Why are we writing 2?
Because there's two different branches here. The first branch is from -infinity to 0. The second branch is from 0 to infinity. There's two branches of that. And then the range, same thing. There are two branches. So from this first branch, the y value from -infinity to 0, and then from 0 to positive infinity. That's what I got. I prefer you put the union, because you're gonna have to make that a habit in pre-calculus and calculus, because that's the expectation. Yeah, I would prefer you put the union just to get used to it. All right, let's move on. Let's do some more practice. So I already did this on Desmos, right? Like, for example, I mean, I'll go back again to Desmos. So you have 1 over x, 2 over x, 3 over x, 4 over x. They all stretch when you do that. So what happens is that, what do you notice? When only a changes, the graph experiences a vertical stretch. Or shrink if a is less than 1.
But the lines will never cross the actual image, the actual axis.
Right. Yeah, exactly. So domain, so that's the other thing we'll say too. Domain and range. Yeah, domain and range stay the same. And if you sketch this graph, I'll do the quick sketch down here. It's gonna be reversed. It's gonna be like this. Reflect about the x-axis. They stay the same. And that makes sense because if you put a negative out front, guess what? What happens if I plug -1 now? What's -2 divided by -1? 2, right? I should be above the x-axis, right? What if I plug like, say, 2? If I plug 2 was y equal -1. Now it should be below the x-axis when x is positive, right? So things flip when the a value is negative. And if I go to Desmos really quickly, you can see that for yourself. If I put negative out front, flips over. Okay, questions so far? We're good? Okay. Now let's actually do some major transformations. So you have your parent function, which is a over x, or I call it 1 over x. You have h, which is the horizontal shift, k, which is the vertical shift. You guys know this by now. And the asymptotes will be h and k. So actually, in this case, h is going to be the vertical asymptote. Just so you know. K is going to be the horizontal asymptote. Now you know. It seems a little counterintuitive because h is a horizontal coordinate, but it actually impacts the vertical asymptote. K, which is a vertical shift, actually impacts the horizontal asymptote. Yeah, good. Oh, sure, yeah, go ahead, yeah. No, if that's what the y-axis, it was flipped.
But it went to the bottom right corner.
Yeah, no. So actually, well, no, hold on. Technically, no, technically you're right. But once we start shifting the graph, so you are correct. It did both that. You can see it either way. But the proper way to say it over the x-axis is if I start moving the graph left or right, then I have to flip over the x-axis.
We just read the x.
Yeah, right. So technically you are correct. It actually did either one. That's a good observation. But in general, for other types of situations where now I'm moving left and right, up and down, and I'm doing a flip, I have to say it's over the x-axis. So, but good observation, because the negative could have gone directly to the x too.
If we wrote that it flipped across the y.
You wouldn't be wrong in saying that if it was just, if you're comparing 2 over x and negative 2 over x, you're not wrong in saying that. You are correct. But I would prefer to just say flip over the x-axis, because that's what's going to happen for the other problems we'll do down the road. So, all right. So here's another one, right? So let's plug in the parent graph is this, y equals 1 over x. And the transformed graph is over here. The parent function is easy. For y equals 1 over x, you get negative 1/3, right? Negative 1/2, negative 1, undefined, 1/2, 1/3. Okay. Now let's look at the transformations. What's h and k here? H is 3. So always counter. I know. Count, and k is what? 2. So what you're going to do, here you're going to add 3. Here you're going to add 2. So if I add 3, I'm going to have 0, 1, 2, 3, 4, 5, 6. If I add 2, oh boy, 5/3, 3/2, 1. It's undefined still, because if you plug in 3, you're going to be divided by 0. 4, yeah, then I get 3. Gosh, that's ugly. I can do better than that. Sorry, guys. 3, 2.5, and 2 1/3. Okay, so let's plot the points.
Could
0.
you write 2 and 1/2?
Sure, same thing. So you have this. You have this. You have this. And then you're gonna have an asymptote right here because it's undefined. And then the other one, you're gonna have 4, 3, 5, 2.5. So the graph's gonna look like this. where you guys think the horizontal asymptote's going to be? Yeah. Your horizontal asymptote's at y equals 2. That's your HA for short. And x equals 3 is your VA, your vertical asymptote. How do I got the points? So it's a little confusing. Let me remove the green curves. Okay, so you see these little red dots, right? So the asymptotes are most important. Actually, I probably should have done that first. I'll do that first for the future problems we do. So you see that the graph shifts 3 right? So the vertical asymptote goes 3 rights. From 0. And then the vertical shifts +2. So horizontal asymptote goes up 2. Now, the boys might be able to relate to this. When I taught this about 17 years ago, this is before all these fancy video games. I casually play video games actually in my 20s. I don't play anymore now. My wife was not like that. But there was a video game called GoldenEye on Super Nintendo or Nintendo N64 that was like a shooting game. So what shooting games do you guys play? I know I shouldn't be talking about shooting games at a school. So anyway, but what are some like Call of Duty, right?
Are you talking about the scope?
Yeah. You know how when you aim and there's a scope? Think of it like that. Like the crosshair, right? So yeah. So anyway, so sorry I was being a little sexist. I think girls probably play too. Okay. But I just hope my son doesn't pick up video games, but we shall see what happens 10 years from now. Anyway, think of it like that. So you have to like position
everything. So, and where the asymptotes intersect, just basically can be, right?
Right. Right. Okay. Yeah, pretty much. So what you do is that after you plot the points, right? You want the curves to get close to the asymptotes, but not past it.
My points go like this.
Here. You could have plotted wrong, yeah. That happens. Okay. Here, hold on, guys. So Elizabeth, your points should be like that. They should be, if you plot it correctly, they should look like that. So you may want. I'll come and look later. So look, don't worry about it for now. We'll fix it later. Okay. Because we'll do another example. So anyway, that's how the graph looks. Now another way to think of this too, guys. Do you guys ever go bowling every once in a while? Okay. If you're a terrible bowler, usually what happens if you're a terrible bowler, they bring out the bumper lanes, right? That's kind of embarrassing. Hopefully you're not one of those bowlers, but if you are, so be it. But think of like bumper lanes, right? These are kind of like the bumper lanes too. Think of like that. Like, it's these boundaries, right? Okay. Domain range was going to be negative infinity to 3, union 3 to infinity. Combined. I didn't make the rules here, guys. I didn't make these math rules. It's a notation. Yeah, I'm just exposing to the notation so that you're not confused and move on to higher levels of math. So it just means combined. So yes, correct. Right. So now we could do this. We don't even have to graph these. We could just well, the parent graph in each case, just y equals 1 over x. That's easy. And then let's do a little table here.
Does that mean it's going to be -1 to infinity for the first one, and then infinity to negative?
What was that? Table. Just make it easy. Just state the asymptotes. I could write like HA and VA 6 more times. I'm just saving time. I'm just making a table. Okay, fine. Fine. I don't have to do that. Fine, I'll just do this. Whatever, guys.
I saw when you're trying to say HA.
Horizontal asymptote. It's an abbreviation. Horizontal asymptote. I was trying to make it easier on you guys, but whatever. Let's move on. No worry. You're good. We'll just be more explicit. Okay, here we go, guys. Does this make sense what I just did? Yeah. HA is horizontal asymptote abbreviated, VA is vertical abbreviated. So you look at what's on the outside, that's going to have how the graph's going to shift vertically. So the horizontal asymptote will be moving up and down, obviously, right? So that's y equals -2, y equals 3, and y equals 5. For the VA, x equals -1, x equals -2, or x equals 2.
So would it be negative for the VA on A would be negative
Yes.
infinity to 1 and then 1 to infinity?
Right. And also, another thing to keep in mind, these are excluded x values. These are x values we can't have. You can't plug in -1 to this. You can't plug in -2 to this. You can't plug in 2 to this. That's why those are your VAs. HAs are basically what shifting of going up or down. It's also the y values you can't have also. Like y here can't equal -2 because 5 over x plus 1 can't be 0, right? This right here, this first fraction, 5 over x plus 1, not equal 0. You can get close to 0, right? I can make this close to 0 if I make x like 1,000,000. This gets close to 0, but a number close to 0 minus 2 is not -2, right? It's like -1.9999999 or -2.001, right? It gets awfully close. So that's what's happening there. Okay, let's do some practice problems. Once you get the hang of it, you guys will move fast on this. Okay, so I'm not going to do the parent graph. I think we're just going to kind of just. I think we. So what's H and K here? So let's draw your asymptotes. So you have your asymptotes are going to be x equals -1 and y equals -2. If that makes sense, x goes with h, y goes with k. Hope that makes sense, I guess. So you're going to graph your asymptotes. So it's like the crosshair in these video games that involve shooting. Go ahead. No, you're not. Okay, good. So what I would do, I had to kind of show you how these were being constructed in a little more labor-intensive fashion, but now we're going to be more efficient. Well, now you see what's happening here. You know that's a vertical asymptote, the -1. The -2 you know is a horizontal asymptote that goes, shifts graph up and down. So now you have that. You know the curves generally don't draw this yet. We're going to be more precise. But you know the curves generally going to look like this, right? That's generally how they're going to look. But let's be a little more precise. So what I'm going to do is plug in numbers for x that I'm interested in seeing. I'm interested in knowing x equals 0, x equals 1, and x equals 2. Why do you think I'm interested in knowing those x values? Because they're pretty close, right? They're pretty close to the asymptote. 0, 1, and 2 are pretty close. What other ones do you think I should look at as well? How about -2? I'm not going to do -1 because it's undefined. Because you can't divide by 0. I'm also going to -3 and -4. Because those x values are to the left. 6 is usually good. You want 3 on each branch. Oh boy. And then if you plug in 0, I know I get 3. 5 minus 2 is 3. If I plug in 1, I get 5 halves minus 2, which is 1/2. If I plug in 3, I get 5/4 minus 2, which I think is. What was that?
2. You gotta plug in 2.
2? Wait, what did I do wrong? Oh, you're right. You're right. Thanks. I get -1/3. Is that right? Yeah. So I have 0, 3, 1 1/2, 2 and -1/3, So graph looks kind of like this. If I plug in -2, I think I get -7. If I plug in -3, I get -4.5. If I plug in -4, I think I get -11/3, which is -3.33. So graph does this. Domain's all real except -1. Range is all real except -2. So that's how you do it more efficiently. Get the asymptotes out of the way. Figure out what exports are going to plug in. You could do the shifting if you want. You could, if you want to do the parent function, you could do that. It's just a lot of math you have to do. I mean, you're doing some math anyway. It's up to you. I mean, if you did y = 1/x, and then realize you had to multiply y by 5 and subtract 2, and then add and take away 1 from x, I guess you could have done that also. But no, we're not going to do all of them. No, we're not. Let's do one more. I don't have to do 3 and 4 because I think you guys kind of get the point. Let's do one more, guys, and then you guys can do the classwork.
What if it was like y equals x?
That is next week. That's next week. Well, that's y = x, but we're gonna do like y = like x plus 1 or x plus -2. That's next week. Okay, one more sec, guys. So let's not worry about the parent function. What's h and k here?
H is -2 and k is 3.
So your vertical asymptotes are x = -2 and y = 3. Okay. So -2 is right here. So it's like your crosshair in the video games, right? You got to aim first, right? Where you shoot. Okay. We're talking about hunting, by the way. Maybe, or going to the shooting range. Okay. We're a little more PC here in California about this stuff. Anyway. Okay. If I was like in Wyoming, you guys wouldn't care. All right. What about Wisconsin? What about Wisconsin? I know.
She's saying Wisconsin's really good for shooting.
Oh, okay.
She was done.
So red state. There we go. Well, Wisconsin's kind of they're kind of blue reddish. Anyway. They're swing state. Swing state, yes. So, all right. What's going on? I don't know what's going on.
No, it's not. An intern is a person.
Okay, guys, let's settle down, please. And you know what? I'm gonna change things up a little bit. You know what? I think this might be a little too much to do 6 points. Let's do 4 points. Let's do 4 points. 2 on each branch. 2 on each branch. Well, thanks. All right. Let's do -1. That's gonna be
Oh my god.
-5 + 3, which is -2. And by the way, if your points are off, that's because you probably made a arithmetic error, right? If you plug in -1, you have 1 in the bottom. -5 + 3 is -2. So -1, -2 is right here. If I plug in 0, what do I get? I think so. Yep, you get 1/2. Very good. Yep. So I know the curve is going to look like this. Ultimately, it's going to curl up towards the horizontal asymptote. Now, when we plug in some values to the left of the vertical out, let's do like -3 and maybe -4. If I plug in -3, I get 5 + 3, which is 8. So -3 comma 8 way up here. If I plug in -4, what do you get? You get 5/2 + 3, which is what? 5.5? Yeah, or 5.5. There you go. Domain's gonna be all real except -2. So these are extremely consistent, just so you know. They get weird next week. For now, they get consistent. For now, they're consistent. Yeah.
And this is direct here.
No, inverse.
Oh,
Inverse.
no, this is inverse.
It's all inverse.
What you're doing.
Because as x gets bigger, well, actually, these specifically, especially +2, they kind of that's but it's a form of inverse gradation. Yeah. Okay, so I'll stop with the notes there. I don't think we need to do page 8 or page 9. I just want to make sure you guys get enough done.
I feel like I already got enough on the practice part.
You know what? If you guys want to just go straight to the homework, let's go straight to the homework, guys. I think you guys get the idea. Yeah. Well, I'm in a good mood because I think the Warriors are going to close out tonight. So, hold on.